So I want to talk about dynamics and rates. Leading to tidal disruption events. So, I'll tell you roughly what a tidal disruption event is, though you'll hear much more about it from Elena later on. And then we'll try to estimate the rate at which these events occur in our galaxy or in any other galaxy. And we'll have to introduce the notion of a loss cone, which could be either empty or full. We'll calculate the relaxation timescale. And I will only do two-body relaxation. Though there is more fancy stuff, which is called resonant relaxation of all kinds. And it's important at some places. And if there will be time, I will also try to explain what is the rate of tidal disruption events as compared to the rates of MRIs. MRIs are extreme mass ratio in spirals. So this is the black hole in the galactic center and a star going around it, emitting gravitational waves and getting closer to it. If I'll have time, I'll do the calculation. If not, I'll just tell you the answer. Okay. So we have, maybe we should put some numbers in here. Let's keep them here. What do we have in our galactic center? Let's take our galactic center as an example for the numbers. Okay. We have a black hole mass of 4 times 10 to the 6 solar masses. How do we know that? Genzel told us, yes. How did he know that? Observing the orbits of stars in the galactic center, orbiting around the black hole. Some stars have completed already a full orbit, some even more. Some have done partial orbit, but had enough observations to fit for that orbit. And if you measure that orbit on the sky, so you see the size of the orbit and the duration, then from Kepler's law, basically you can get the mass of the black hole. Now this is not exactly right, because when you see the size of the orbit on the sky, it's not the real size of the orbit. You know the size up to a distance. You don't know the distance to the thing. So if you just measure the size on the sky, you cannot tell the mass of the black hole. But if in addition on one point in the orbit you measure a velocity, that allows you to understand what is the distance to the galactic center. Therefore, we measure by observing those stars and their velocities, both the mass of the black hole and the distance to the black hole in the galactic center. It's about 8 kiloparsecs, 8.2. Okay. This mass is embedded in some distribution of stars, okay? And it affects the distribution of stars very close to it. Oh, I wanted to talk about that too. This is called the Bacol-Wolf cusp. This is the distribution of stars that formed around the black hole because of the gravity of the black hole. Okay, so you can think of the galaxy as a bath of stars. Then you put a 4 million solar mass black hole in the center of it. It attracts more stars around it, and there is a cusp of stars. And we'll have to understand what is that cusp, because it will maybe affect the rate of these interesting events. Okay. What else do we know? Most of the stars are about 1 solar mass. So we'll assume that, and we'll ignore the important fact that the stars have a variety of masses, and this actually play between different masses of stars in the galactic center does have an important role, but we'll leave it for now. We have the area around the black hole in which the mass of the black hole is the dominant mass. So there is a black hole in here. I'll plot it here. And there are some stars around it. Close to the black hole, most of the mass is that of the black hole. The farther you go, you collect more and more stellar mass that are engulfing the black hole. Eventually, at some distance, the mass of the stars and the mass of the black hole are equal. We call that the radius of influence of the black hole. Okay? How many stars are within the radius of influence? 4 million by definition, right? Because each one of them is one solar mass. And okay. So we call that distance RH. It's about 2 parsec. If you're doing things for which GR is relevant, so for example, if I want to understand these MRIs, or if I want to understand GR effects on precession of orbits and all that stuff, then I care also about the Schwarzschild radius of the black hole. And it turns out, accidentally, so the ratio of the mass of the black hole to the mass of the star is 4 times 10 to the 6. But also accidentally, the ratio of the radius of influence to the Schwarzschild radius of the black hole of this mass in our galactic center is also 4 times 10 to the 6. Just an accident. So there are 2 4 millions in this problem by accident. Okay. Another important number is the period of a circular orbit or any orbit with a semi-major axis equal to the radius of influence of the black hole around the black hole. Okay, so if you put a star in here, you ask how long does it take to go around. This is 10 to the 5 years. Okay. So all these stars within the radius of influence have had many orbits by now. Wherever they are, they went around the black hole 1,000,000 times or slightly less, 10,000 times. Okay. Okay, so now about tidal disruption. What is a tidal disruption? If you take a star too close to the black hole, so that the differential gravity of the black hole on the 2 sides of the star is stronger than the self-gravity of the star itself, then the star tears apart. So let's write that down. So the gravity of the black hole on the star is gm over the tidal radius, which we are trying to calculate by this equation, square. This is the force between the black hole and the star, or the force per unit mass. But if I want the differential force, because this force doesn't do anything to the star. If the star is there, it just free falls with this acceleration. So if that force was uniform over the whole star, nothing would happen to the star. It will just accelerate. But if the force is differential, if it's not the same force on all the parts of the star tears apart. So the difference between the forces on one side of the star and the other side of the star are different from that by this amount. They are a small fraction of the overall force that the black hole is putting on the star. When this is equal, the acceleration or the force per unit mass of the star itself, then the star is marginally being torn apart. So you see from that, the G cancels, that the tidal radius is the radius of the star times m over m to the 1/3. Okay? So this is about 100, right? Because this is about 1,000,000 to the 1/3 is about 100 or a little more. 100 times solar radius is about an AU. So the tidal radius, let's keep it here. The tidal radius is 1 AU. The Schwarzschild radius what do you remember? You remember the Schwarzschild radius of our own sun for solar mass black hole? What is it? 3 kilometers, okay? And the Schwarzschild radius is proportional to the mass. So it's 3 kilometers times 4 times 10 to the 6. Let's do the calculation. 3 kilometers. So now it's in centimeters. So what do I have? 12 times 10 to the 11. So 10 to the 12, right? So that's 0.1 AU. So 10 times smaller than this. So there's not much room between the Schwarzschild radius and the tidal radius for a solar mass star. Okay. So now the question is, how many stars do approach the black hole to within this distance? Right? They get somewhere between this distance and that distance. Then they will be torn apart. What happens after they're torn apart and so on, you will hear a lot in this conference, starting from the next talk. Right, Elena? Okay. Good. So let's suppose that the orbits of the stars in here have an isotropic velocity distribution. They scattered each other, and they got into isotropic velocity distribution. How many of them are going to have an orbit which is elliptical and gets all the way to the black hole to within that distance? What is the fraction of the orbits that are going to have a small distance approach, a periapse of that much or less? So you can work it out by conservation of angular momentum. Right? So we have some velocity here at the radius of influence, and the angular momentum per unit mass of a star that is there is the orbital velocity times that radius of influence. Right? Velocity times this is the angular momentum if the velocity is perpendicular to the distance from the black hole. So for a circular orbit. What is the angular momentum that I need in order to get to this small distance? Well, I know that okay, so I can write it actually differently. I know that angular momentum as a function of distance on Keplerian orbit scales as what? How is the angular momentum of Keplerian orbit scales with distances? You just say different things like angular momentum for Keplerian orbits. No. Square root of r. Okay, good. So actually I don't need this. The angular momentum of an orbit that will come into here is smaller than that of a circular orbit over here by the ratio of the tidal radius to the radius of influence to the square root. So only stars that have, when they're here, angular momentum that is smaller than that of a circular orbit by that amount, which is a huge amount, will get close enough to the black hole. Now you have to imagine this amazing kind of orbit, right? This is an orbit that comes from this distance, 2 parsec, to the tidal radius. The ratio between these two is 10 to the 5, 10 to the 6. Okay, so it's an amazingly long orbit. These are the orbits we're talking about, and they are rare. They need to have angular momentum smaller than the typical one by that much. And if you think of the two-dimensional velocity distribution that determines the angular momentum, why two-dimensional? Because the component of the angular momentum along the radius doesn't matter, doesn't give any angular momentum. You need the two components perpendicular to that. So it's a two-dimensional phase space. So the number of orbits that will have that, if the velocity distribution is isotropic, is the square of this. Okay? So the fraction of orbits with angular momentum less than this out of the circular angular momentum is the square of that. You got the square here? It's just the fact that I need two dimensions of the velocity. And this is a small fraction. Right? We said that this ratio is 4 millions. And the tidal radius is about 10 times than this. So this is instead of 4 times 10 to the 6, 4 times 10 to the 5. So how many stars, if the velocity distribution is isotropic, at any moment have such a small angular momentum? Okay? So how long will it take them to get tidally disrupted? They need 10 to the 5 years to do one orbit. So every 10 to the 5 years, if this was the situation, we'll have 10 TDs. Okay? You can think of that as the upper limit of tidal disruption event rate. And the calculation I've just done is the full loss cone case. I'll explain what the loss cone in a second. Okay? So what is the calculation we have just done? We took the number of stars. We asked which fraction of them have this small angular momentum so they can get that close to the black hole. It's RT over RH. It's that product that someone calculated for me to be 10. And if I divide that by the orbital period, this is the rate of tidal disruption events. Now, the number of stars is nothing else but the ratio between the mass of the black hole and the mass of the star. Because by definition, we are looking at a distance where the mass of the stars is equal to the mass of the black hole. So another way to write that rate is m black hole over m star times RT over RH divided by P. Okay? So this is the full loss cone case. Now what is this loss cone business? If you think of the velocity distributions in here, they could be isotropic, but if nothing touches the orbits, if there is no interaction between the orbits and each orbit remains Keplerian, then all the orbits that are oriented close enough to the black hole within that amount have already done in the first 10 to the 5 years their orbit. They approach the black hole. They got tidally destroyed, and they don't exist anymore. Okay? So out of all the possible velocities in here, we can take all the velocities who are closer to the radial line pointing to the black hole so that the angular momentum is small enough. And you can think of that as a cone in velocity space for which every star that has a velocity within that cone is destroyed. Okay? And if there would be no interaction between the stars, they have already been destroyed because the age of the galaxy is much longer than this. And then we'll have an empty loss cone. And then the rate of tidal disruption events will be 0. Nothing more. Okay? So now we have to do exactly the other extreme. The empty loss cone. Okay? So now we want to know how quickly do stars scatter each other to refill the loss cone that the black hole evacuated. Okay. Maybe I should copy this result in here. So the rate here that we got is the mass of the black hole divided by the mass of the star, RT over RH, p to the minus 1. And we still have to find out what is the other equation here. And for, let me just write that for the parameters of our galaxy, this is 10 divided by p. Okay? Okay, so now I'm doing the empty loss cone. So who scatters the stars? The other stars. Since I know how many there are, I can calculate the scattering rate. I know the forces between them. It's all super easy. Let me keep those numbers. Maybe I can remove this. Okay, so let's say I have two stars. They're moving around the black hole, but they're not moving like in a disk all in the same way. They're moving in random directions. So the relative velocity between them is the orbital velocity around the black hole. So when they pass at some impact parameter b, from each other, they stay at that distance b for a time b divided by v orbit. Within that time, they put acceleration on each other, which is gm over b squared. So this is the acceleration times the time. It's delta v that they get when they pass next to each other. And I can therefore calculate the change in the angular momentum that they exert on each other, which is this times the radius of influence, if that interaction happens at the radius of influence. So what did I get here? Gm over b RH. V. And the H should be an index like this. Okay. So now if I'm waiting some time, and I want to know what is the rate of interactions with a distance b, so I'm going to multiply the cross-section by the velocity, by the density. It will give me the rate. So the rate of interaction of this kind is pi b squared. I'm not going to really keep the pi. I'm just writing it for you to know where the b squared came from. So pi b squared times the density of stars, which is n star divided by RH cubed, times the velocity. This is the orbital velocity around the black hole at RH. So what did I get? Well, more or less what there is here. B squared, n star, v orbit over RH cubed. So now the motion of stars in that situation is sort of diffusive in the angular momentum space. They sometimes get a kick in one way, sometimes get a kick on the other way. And if I want to calculate okay, I can calculate a diffusion coefficient. This is the way it's usually done, but maybe I want to skip it. If I would like to calculate a diffusion coefficient, I will take the square of this angular momentum, multiplying it by this rate, and I'll get something whose units are angular momentum squared divided by time, and that would be the rate of diffusion, or the diffusion coefficient for the angular momentum. Instead, maybe I should ask, how close of an approach should I have in order to completely deflect my orbit by 90 degrees? Okay? Let's calculate a specific B. I'll do the diffusion coefficient in a second. So if I want to come close enough on a short enough B so that my deflection will be 90 degrees, completely change my orbit around the black hole. So we calculate the change in velocity. Here it is. When this is equal to V orbit, then I have a 90 degrees change in my, so B mean can be calculated from equating this, gm over b v orbit equal v orbit. So B mean is equal to gm over v orbit square. Now look, what is G capital M, mass of the black hole, over v orbit square? What is G capital M over v orbit square? RH, A, yeah, the semi-major axis of this orbit. So this is smaller than RH by M over M. Okay? So the typical distance between stars at RH is RH. But if you want to have this huge deflection, you should get closer to some other star by about 1 million. Okay? Very close interaction. It's rare, but it happens every now and then. And that will give you a complete scattering. So basically, the velocity distribution should be reconfigured completely, or isotropized completely, over this time scale, over the time scale for which these interactions occur. So let's calculate that time. We can do that from this rate, putting in this B. Okay, so this is the rate at which interactions with a given B occur. This is the B that is needed for a complete deflection. And I'm asking what is the rate of that. And the inverse of that rate is the relaxation time, up to a small logarithmic factor that I will come back to. So the relaxation time is the inverse of this rate, with B being this. So we have M over M square, RH square, and then the rest of this. N star, V orbit, RH cube. I don't know why I put this parentheses. Okay, so I squared this, because there is a B square here, and then I just copy the rest. N star, V orbit, RH cube. Oh, because I want the inverse of that. Yes, that's why I put it. Okay, so let's see. At the radius of influence, N star and M over M cancel, right? Because the number of stars is the mass, is the ratio between the mass of the black hole and the mass of the star. So what I have here is M over M to the minus 1. And then I have RH over V orbit, which is what? P. So this is basically the relaxation time. Okay, so the relaxation time is longer than the orbital time by M over M. So it's about 1 million times the orbital time, so about 10 to the 11 years. So slightly too long for the age of the galaxy. Okay, the galaxy is almost relaxed. The inner parts are more relaxed than the outer parts. Well, that gives you the idea. Now there is a logarithmic term that comes in here. And why? Because here, the calculation I've done is that of a strong deflection. But I told you I can actually do diffusion by many smaller interactions. And if I will do that, if I wanted to calculate the diffusion coefficient, I should have taken the rate of this times the angular momentum square that they do. And if I take the square of that and I multiply by that, I will get something that is independent of B. Right? Because the square of this and this, they cancel out. What does it mean? It means that the diffusion of angular momentum over orbits of star is dominated by all scales, very short encounters, like the one I've calculated here, but also very distant ones that are very, very frequent. Each one is doing a very tiny deflection, but when you count them all, they contribute the same to the diffusion coefficient. So actually, the time scale is shorter than this by a factor of a few, counting how many scales contribute to the diffusion coefficient. Each one of them is doing the same work. So basically, the relaxation time is smaller than this by a logarithmic factor, which is the ratio between the smaller encounter you can think and the largest one you can think. What's the smallest we can think of? This one. What's the largest we can think of? RH. What's the ratio between them? So it's the logarithmic term of a few millions. So what is it? 10, 15. Okay? So here we got 10 to the 6, 10 to the 5, 10 to the 11. And with this, it's about 10 to the 10, just about the age of the galaxy. Okay, so this is the relaxation time. Within this time scale, if nothing else happens, you evacuate the, you redistribute the velocities completely. You will isotopize them. Okay. But this is a long time scale, you should remember, right? It's 10 to the 10 years. How long does it take to empty the lost cone? 10 to the 5 years, one orbit. Every star that has an orbit with minimal approach smaller than RT will get destroyed. But in order to refill the lost cone, I don't need to isotropize all the velocities, because the only thing the lost cone destroys is a tiny fraction of the angular momentum. So I need only to isotropize the angular momentum within the, where did I write that? The tiny angular momentum that the lost cone has, which is smaller than the total angular momentum by RT over RH square root. Okay, so let me explain that. So this is the time that it will take to completely change the velocity of an orbit, from an orbit that looks one way to an orbit that looks completely differently. But I don't need to do such an extreme job. I only need to change the angular momentum by a small amount, which is delta J to refill the lost cone. Change in angular momentum, we said it before, it's RT over RH square root out of the circular angular momentum. So diffusion, as you know, goes as the distance that you go in a diffusion process goes as the square root of the time, or the time in order to get to a certain distance goes as the square of the distance you're trying to traverse. So at this time, the relaxation time, you can change the angular momentum by the circular angular momentum, because you can completely change the orbit. If you just want to change it by this little amount, so you'll have to do delta J over JC square out of this time, because it's a diffusive process. Okay? So let me say that again. If I know that over a certain time my diffusive process can move a particle from here to here, either physical space if it's physical diffusion, or angular momentum space if it's what we're talking about here. If I know that in this time I can move from here to here, if I only want to move a tenth of that distance, I will have to wait 1% of that time, because diffusion goes as square root of time, or time goes as square of the distance you want to go. So I need to do this divided by that square. times this will give me the time that it takes to fill the loss cone. So, so the time scale that it takes to fill the loss cone is about RT over RH times this time, M over M, times P, divided by that logarithmic factor. So let's see, what did we get here? This ratio, if it was the Schwarzschild radius in here, instead of the tidal radius, it will exactly cancel this ratio by accident. That's the same, the 2 4 that we had here. But this is the tidal radius, which is slightly bigger, so this times that is 10. This is about 10. This is one orbital period, so what we got here is roughly P. So what does it mean? Is the lost cone empty or full? Is that scattering rate good enough to refill the lost cone or not good enough? What's our conclusion? Just on the edge, okay? So on every 10 to the 5 years, every star that had angular momentum small enough to get destroyed is destroyed. But on 10 to the 5 years, you can just refill the loss cone. The calculation should be done a little bit better. In the actual calculation for the time scale that it takes to refill the loss cone, this logarithmic term disappears. I will try to explain why. Let me say that in words. Once you have evacuated the loss cone, if you left the edges of the loss cone completely full, this would be the correct calculation. But after a while, they're also getting diluted a little bit. And now you need to bring stars from a little bit farther away, so you'll get some equilibrium profile of the angular momentum distribution that will make the process a little bit slower than what I have here, and it's only by a logarithmic factor. Okay, so the time scale will be longer than this by this logarithmic factor, and we'll get that the loss cone is on the empty side, but marginally so. Okay, not in a big way. Okay, if I want to do this diffusion, let me write it. I'll take this off. It turns out that diffusion in 2 dimensions has a very peculiar property. Why am I saying 2 dimensions? Because there are 2 components of the velocity that I'm trying to diffuse, because only 2 components of the velocity contribute to the angular momentum. The radial one doesn't. So you can think of this problem. There is some bath of whatever you're trying to diffuse at some external position. So this is position in a general diffusion problem, or angular momentum in the problem we're interested in. And these are the stars outside of the radius of influence. So they're not completely bound to the black hole. They're bound more or less to themselves. And they set the density of objects far away. And if you dictate minimal angular momentum, who is the square root of RT over RH times the circular angular momentum. Okay, so the ratio between those two is a few thousand, 2,000, or maybe just 1,000. And you're saying that there is no particle in here. You will maintain some equilibrium shape of the distribution between this point and that point. If this would have been in 1D, what will be the distribution? No, I'm asking, I have a distribution of some material that is going through diffusion. Let's say I have a diffusion of a particle of some kind, smoke, in this room. I have a certain level of smoke here, and here I have something that clears the smoke, zero smoke in here. And now there will be diffusion of the smoke from here to here, but whenever it comes here, I empty it. So there is no smoke here, there is full level of smoke here. What is the distribution in between if it's in a planar symmetry? Linear, right? Because I'll need to have a constant flux from here to here. This is in 1D. So the flux, if you want to think about it this way, this is the distribution function. The flux is the derivative of the distribution function times the diffusion coefficient, that is the flux. And this is constant, meaning that f is a linear function of j. But in 2D, how do you calculate the flux? It's j times d times df dj. Right, so you can now think of rings. So suppose the same smoke story that we had before, but the smoke is distributed in a 2D plane in a ring, and I'm evacuating the smoke from the center, so from some small ring in the center. So now the smoke is trying to diffuse through these rings, but as it is getting to smaller and smaller rings, it is harder to diffuse. There is no surface area there. And the flux is still given by the derivative of the occupation number times the diffusion coefficient times the area or the length of each ring, which is proportional to j. If it would have been diffusion in 3D, there would have been a j square in here. So this is 1D. That is not relevant for us. This is 2D, which is our case. So if you solve this, you get that f is a logarithmic function of j. And since it has to be 0 at the loss cone, I know that it looks like this with some arbitrary coefficient in here. So the function is not like this. It's more like this, which is this function. Okay, so these are all small corrections if you want to get it completely right. And I will roughly skip that. The answer that we got in here for the empty loss cone case I deleted that, but it's basically p to the minus 1. So you see, these two cases are not that different. If the loss cone is completely full, if somehow the scattering is super efficient, we expect 10 TDs per 10 to the 5 years. If the loss cone is empty and we're building on the two-body scatterings of stars to bring them back into orbits who gets close enough to the black hole so that they can be destroyed, we'll get 1 per orbital period at the radius of influence of the black hole, which is 1 per 10 to the 5 years. Okay? And in our galaxy, we're closer to this situation than to this situation. But even if not, the difference is not that huge. Okay. Questions up to here? Yes?
Other galaxies have bigger difference between?
Yes, in principle, yes. Not huge, because there is some scaling of how the radius of influence of a galaxy depends on the mass of the black hole. Basically, if you want, it's the m-sigma relation. And that makes that ratio between those two quantities not that different. But if you could build your galaxies yourself, you could do it whatever you want.
We look for the single star. What about binary? Is the same calculation? About
If you look at the binary as a binary entity, yeah, it's the same calculation. Okay. For a binary, there is a bigger tidal radius because you need to just depends what you want to do with it. If you want the two components of the binary to go tidal disruption events, they will have to go to the same small angular momentum. If you just want the binary to break, they can come to a bigger distances and still be the same. Okay. So all I've discussed in here is the diffusion in angular momentum. What about diffusion in energy? Could these particles come, scatter each other to smaller orbits, and eventually come not on this super weird orbit that comes from 2 parsec and goes all the way to 1 AU and goes back, but actually diffuse this way while they orbit around the black hole, comes very close to the black hole, and eventually get destroyed or get swallowed by the black hole. So is that possible? So in order to understand that, I want to talk about the Bacol-Wolf cusp. So they were trying to answer, Bacol and Wolf were trying to answer exactly that question. Okay? They were trying to think, in a steady state, when I'm allowing diffusion of the energy of the stars, what will be the equilibrium shape of the density of stars around the black hole due to their own interactions, their two-body interactions alone. Okay? So we calculated the interaction time, the relaxation time between particles. And let's do that again. So if 2 particles go g m over, they go on a distance, okay, I want to calculate what is the b for which 2 particles deflect each other strongly. Now I'm not going to do that only at the radius of influence, but I'm going to do that at any distance from the black hole as a function of r, the distance from the black hole. So gm over b squared times b over v. V is now a function of the distance from the black hole. I've done that calculation before for RH. I'm repeating it for any r. So gm over b squared times b over v. I want this to be equal to v. That means that I got a deflection of my velocity by order of the velocity. This changes the angular momentum completely. It also changes the energy completely. So you see just from this argument that the time scale to change the energy and the time scale to change the angular momentum is the same. Okay? So we already know at the radius of influence that it's about 10 to the 10 years. But let's see how it changes at any radius. So this is the impact parameter that we need. B is equal to what? This is what we called B mean before. Is gm over v squared. And then if I want to calculate the rate of these events, so it's the number of stars at distance r divided by r cubed times b mean square times the relative velocities, which is a function of r. This v is a function of r. This v is a function of r. And the inverse of that is the time. Or this is the rate if I don't take the inverse of that. And if I plug this in, so I get n star divided by r cubed, g m v cubed. Right? Okay. So now let's see how can I cancel things in here. G m over r, if it was the other m, if it was the mass of the black hole, then g m over r would have been v squared. So I can take one gm over r that way and write v squared, which will cancel 2 of those. So what is this? This is the inverse time, the rate at which I scatter stars strongly at any given distance from the black hole. So 1 gm over r is v squared, and then I have a gm over r squared still left, n star divided by v, right? And now I have gm over r cubed I will add one r in here and one r in here. R over v is the orbital period. Gm over r cube, if it was the other, oh, I missed, I replaced here m by m, so I have to correct for that. So I have 1p from here. G, if again it was the other m divided by r cube, it was the inverse period square, omega square. So I have p to the minus 2, n star, p, and m over m square. So I have 1 over p, final answer, m over m square, and n star. Let me remind you that this is what we got before, because before, at the radius of influence, n star and 1 factor of m over m cancelled out. So we got the orbital period, the time, which is the inverse of this, was the orbital period at the radius of influence times m over m. That was 10 to the 5 years, and m over m was 10 to the 6, so that was 10 to the 11, and then we said maybe we have to add, not maybe, we have to add a logarithmic factor to reduce it by another factor of 10 or so. Okay, so this is the rate at any given distance, and it changes with the number of stars at that distance and with the period around the black hole at that distance. So now the first attempt to solve the equilibrium state of that was by Peebles, before the Bacall-Wolf thing. And he said the following: if there is a black hole, it absorbs the stars that arrive to the black hole, and the stars from it diffuse at a constant flux towards the black hole on a time scale which is given by this. So he said the following argument: you take the number of stars at a given r, we called it n star, you multiply it by this rate, or you divide by the time, so you get this as the flux of stars per unit time that diffuse out of this semi-major axis. And he said this is equal to constant. You follow the logic in here? Let me say that again. There is a delicacy here. This is not the final answer. That's not the Bacall-Wolf answer. So this argument turns out to be incorrect, but let me tell you the logic again. You look at every radius. You ask how many stars are there at that radius. That we called n star. It's 4 million at the radius of influence. It's probably smaller as we go closer and closer to the black hole. You ask how long does it take these stars to completely scatter each other, to change the energy of any other star by a significant amount. So presumably they would move out of that orbit, in or out, by that time scale. So if you multiply that rate by the number of stars, so I just multiply the rate by another n star, that is the number of stars that are going to be evacuated out of that semi-major axis. And he said that flux of stars is a constant. This will give you an equation for how n star depends on r. This is a constant. P depends on r, as r to the 3/2. So that will tell you that the number of stars at a distance r is proportional to p to the 1/2, which is r to the 3/2, 3/4. And if I calculate the density out of that, density of stars, I just have to divide by r cube. So I have r to the minus 9/4. Did you follow this? This is Peebles' argument, and it's not right. Okay, as I'll show you in a second, Bacall-Wolf arrived at the conclusion that the density is proportional to r to the minus 7/4. Not as steep as this. So what's wrong in this argument? Does this argument tell us where the stars are going, inward or outward? No, it just said there is a constant flux. As these stars are scattering each other from one semi-major axis to another, they also have to conserve energy, in addition to conserving the number of stars, which is what this argument is saying. And as they are trying to diffuse inwards towards the black hole, the energy that you have to transport out for each star that you are trying to scatter further in is getting greater and greater, because the binding energy per star close to the black hole is huge. Okay? Think about it this way. For each star, if you did a diffusive process in energy, for each star that you have swallowed into the black hole, how many stars you have to scatter at the radius of influence to transport that energy outward? What is the binding energy at the radius of influence compared to the binding energy at the Schwarzschild radius of the black hole, or the tidal radius? Not that different. The ratio of the distances, which is 1,000,000. So if you want to do a diffusion here and you want to get off that energy outward, you have to do 1,000,000 times more scattering outside than you have to do inside. So because if you're trying to push stars in, the thing that is going to limit you is not the rate of scattering of stars, is the amount of energy you have to diffuse. So it's the flux of the energy that has to be constant, not the flux of the stars. Okay? So all I need to do in order to get to the right equation is not to say the number of stars times the rate of the scattering is constant, but the number of stars times their energy goes like 1 over r, times the number of stars, times this. So basically I'm copying the same thing, I'm just adding 1 over r. This is constant. And if I do that, I'll get the same thing as before, but 1 more half power of r more into n, and therefore half power of r into the density. And I'll get that the density is proportional to r to the minus 7/4. Where is Elena? You see, this bending down is useful for the talks as well. Okay. So, so this is the Bacall-Wolf profile. What does it tell us? If I want to compare now the number of stars that will come towards the black hole by diffusion of energy to the Schwarzschild radius, how is that going to compare to the rate at which they are scattered at the radius of influence? By a factor of 1,000,000. The same factor of 1,000,000 we talked before. So diffusion in energy, at the end, if you want to go all the way to the black hole, is going to be 1,000,000 times less effective than diffusion in the angular momentum. Okay? So the way they come from the radius of influence to the black hole is on very long, elongated orbits, and very few of them come from the vicinity of the black hole and diffuse slightly more in energy and get swallowed. Okay. So let's see, what did we cover? We covered this, the two-body relaxation. We did the Bacall-Wolf cusp. Wow, we did a lot. Okay, very good. Questions? And then I'm going to do the last thing as well. Yes. I'm saying, what I said is the following. Once we decided that this is setting the profile, I can compare now this, which is no longer a constant, between the inside and the outside. Now this is a constant. This one compared to this is missing 1 over r. So if I compare this in the inside, close to the black hole, at the Schwarzschild radius, let's say, and at the radius of influence, the ratio between them, because it's this quantity that is constant with the r, the ratio of this is the ratio of r's, which is 1,000,000. Okay? Let me say that yet in another way. Actually, this will take me to the next subject. So I'll plot a diagram, and then we'll come back to this point. Okay, so let me plot the following diagram. This is the distance from the black hole, r. And this one here is the periapse distance of an eccentric orbit. This is the line of periapse equal semi-major axis. It's a bit too steep. I only need 45 degrees. This is, of course, not allowed. Right? Because the periapse distance cannot be larger than the distance. What interesting numbers I want to stick in here? Okay, this is the distance from the black hole, and this is the periapse distance. Okay, so if the orbit is like this is the black hole, and I'm looking at the star with this orbit. This is the x-axis, and this is the y-axis. Within a factor of 2. Okay? Okay. So let's see where are the different things I discussed in here on this diagram. Which numbers do I want to put on the axes? Which are the interesting ones? The radius of influence of the black hole. That's the largest thing I'm going to discuss. You can ask why I'm not discussing stars which are even farther away. They can also have the same thing. It turns out this is slower. You can calculate it for yourself. RH, what else? RT. Here is RT. It's tiny. What else? The Schwarzschild radius, a factor of 10 or so smaller than RT. This is RS. Let's put it some. So if we don't do GR, RS is unimportant. If we want to include gravitational waves, RS will come into the game. Okay, the diffusion in angular momentum that we discussed before, the stuff that actually brings the star into orbits which will create TDs. Where is it in this diagram? It's at the radius of influence, and they diffuse in angular momentum, keeping their semi-major axis fixed, just making a more and more elongated and narrow orbit. So they start here on roughly circular orbits with semi-major axis and periapse distance of order RH, and then they diffuse in angular momentum, which means they diffuse in RP, going down towards here. Once they come here, they get destroyed. So they don't get all the way to the Schwarzschild radius, they do it this way. Okay. What is the other diffusion we were trying to make, or Peebles was trying to make? And Bacall and Wolf corrected to this power law. Where is all that stuff? This doesn't have any angular momentum in it. It assumed roughly circular orbits, which is the majority of orbits. Where are the circular orbits in this diagram? On here. So you can also have diffusion this way. If you will put a bunch of stars here and ignore the rest of it, they will scatter on the relaxation timescale of that place, which is the t to the minus 1 that we have written in here. But if you want to know what is the net flux of particles that are going inward, it is much smaller than that, because at this critical density profile of Bacol and Wolf, the actual flux of stars is 0, if the profile was exactly this. Okay. You can also have diffusion in angular momentum any other place you want. So also stars from here can diffuse in angular momentum and get destroyed. You can calculate the rate of that, because we know how many stars are in here, because we have the Bacol-Wolf profile. So I know the number of stars at any given distance from the black hole, and I can redo the calculation. And I will get, if I'll do that, actually we've done that, because this is the rate at which you scatter all the stars, or the number of stars you scatter per unit time, at some position r. But we build the profile, the r to the minus 7 quarters, so that this is constant, not this. So this is different than that by 1 factor of r. That's again the answer to your question. Okay? So what does it mean in this diagram? It means if I'm asking what is the rate of stars that are going this way and make tidal disruption events here, coming not from the radius of influence but farther in, compared to those coming from the radius of influence, the ratio between this rate and this rate is just the ratio of radii. Super simple result. Because what we got conserved around here is not the flux of particles, but the flux of energy, which is 1 power of r different than the flux of particles. Okay. What do I have? 10 minutes? Who is the chairman? I'm the chairman. Okay. Yes, so I have 10 minutes. Say that again?
Your answer is also dependent on your radius.
Yes.
So if your answer is dependent on radius, then there will be extra dependencies in the ratio.
No. N star depends on the radius according to this equation. And the rate at which you scatter the stars per unit time, is this. So the way that n star depends on r is already taken out of this equation, and I'm just comparing this to that. And the difference between that is just this power of r. Okay? Let me say that in different words. I build a profile of roughly circular orbits on different distances from the black hole such that the flux of energy is constant. And that means that the flux of stars is going like 1 over r. Because the ratio between number and energy is just 1 over r. So if I build it such that the flux in energy is constant, the flux of star is going like 1 over r, or going like r. So there's small flux here, smaller even flux here. Okay. 10 minutes, I'm not sure I'll have time to do, we can try if I can do the full thing. Let me give you the bottom line, and then we try to work it backwards for how long we have time. I can now compare the time scale that it takes gravitational waves to change the apoapse of such an elongated orbit. Okay? Not a hard calculation, very simple one. And I can compare that with the time scale that it takes such an elongated orbit to diffuse its periapse. Okay? So let's say that again. Think of an elongated orbit far from this diagonal line, somewhere here. Two things happening to it. Two body scatterings at the apoapse change its angular momentum, therefore changing the periapse. By a tiny bit, a small change in the angular momentum can change the periapse significantly because the periapse is tiny. There is almost no angular momentum in that orbit, so any change in the angular momentum is significant. This is the up and down motion that we have in here. Okay? On the other hand, gravitational waves of very eccentric orbits, they happen mostly in here. They emit energy and angular momentum in here, and they shorten the apoapse. Okay? So this diffusive process that we discussed is moving particles here up and down, while gravitational waves, what do? They move to the left, non-diffusively. They keep the periapse distance fixed, and they shorten the apoapse. And I can calculate the rate of those two, and if we'll have time, we'll do that, and equate them and find where these two are equal. And it turns out, very surprisingly, that the line that separates gravitational wave timescale dominates from two-body interaction dominates always go through this point here. The radius of influence and the Schwarzschild radius, regardless of the parameters of the system. And it has a slope of a -half. Okay, we can calculate that if we'll have time. So over here, it's two-body interactions. Over here, it's gravitational waves. So let us pick a particle and decide what's going to happen to it. Let's say this guy here. It's already on a slightly eccentric orbit because it's below the top line. It will diffuse up and down. If it's lucky enough, it will diffuse all the way down and tidal disruption, gone. Okay. What about this guy? Same. Diffuse up and down, tidal disruption. What about this guy? Diffuses up and down, hits this line, turns to the left, becomes a circular orbit. It's still in the place where gravitational waves dominate, so scattering of other stars is no longer important. And it comes here, and it will eventually sort of goes tidal disruption, but in a very gentle way, because now it comes on a circular orbit towards the black hole. It's basically not going tidal disruption, it's filling its Roche-lobe, which is the same thing as going tidal disruption, but on a circular orbit. And it's the same kind of object that Sterl was talking about in the first day, I guess. So these are the MRIs. Okay? So if you take my word for the fact that the line separating, and I'll try to calculate it, that the line separating the gravitational waves and the two-body always passes through here, radius of influence and Schwarzschild radius, and has a slope of -1/2. If you take that as a given, please help me estimate the rate of MRIs compared to the rate of TDs. So who makes most TDs? This channel. Who makes most MRIs?
The ones who go down exactly at the...
Yeah, the one who goes... You have to start as much to the right as you can, but you cannot start here because they will make TDs. You have to start right here, that you come just above the tidal radius, you turn. You can also take those, but there are fewer of those, because we said that the rate everywhere here goes like the ratio of the radii. Okay? So basically, this thing that I was asking about, the rate of MRIs compared to the rate of TDs, is a ratio between this radius, which is the radius of influence, where most TDs are happening, to the radius where you hit the boundary between gravitational wave dominance and two-body scattering dominance, just above the tidal radius, so that you can turn left just before you die. Come here and die as an MRI. Yeah, so you might want to lift the tidal radius a little bit. So maybe it's right. If you're worried about what you said, let's take 2 tidal radii. So maybe the line should be a factor of 2 above this, so the star won't be partially destroyed when it comes back, comes to periapse. So you'll move to here. To an order of magnitude, there's no difference. But you're right, in principle, all these interesting phenomena will happen. So what is the, sorry, the ratio between this radius and this radius? Since I told you that this line has a slope of 1/2 or minus 1/2, then what's the ratio between those? It's the square of the ratio between those, which is the tidal radius divided by the Schwarzschild radius. So MRIs are more rare than TDs by the ratio of the Schwarzschild radius to the tidal radius square. Slightly, yeah, another factor of 2 or 4 or something. Yeah, I'm not sure I even have to go twice the tidal radius. Yeah, it will be a factor of something more rare than this. So MRIs are more rare than TDs by about a factor of 100 if the only physics you put in is two-body scattering and gravitational waves. There's more fancy stuff that I mentioned. I think it's not going to change the picture considerably, like all this resonant relaxation. The thing that might change the picture considerably is breaking up of binaries. But that's a story for another talk. No. Yes, all the stars are normal solar mass stars. If they're white dwarfs, they won't go any, right? They will come here. If they're black holes, heavy black holes, they can scatter my stars more efficiently. It changes the whole, might change a lot in the picture. This is a very synthetic. Sorry, what are you referring to? White dwarfs coming where?
Suppose I have white dwarfs, can I get them from RA?
White dwarfs coming in here, their tidal radius will be smaller than the Schwarzschild radius. So they may just barely do that turn.
So there are many more than me.
Yes.
So for Lisa's dwarfs, you get
Right. So if, okay, basically another way to say what you're saying, if RT is smaller than RS, then this breaks, it becomes 1, and you have many MRIs. Sure. But this is the equation still. It's just that if you have white dwarfs, RT is tiny, smaller than the Schwarzschild radius. Questions about this before what can I do? We can try to derive this line. Okay, let's try to derive it. This is the time that it takes at any given radius to change the orbits of circular orbits considerably. One last board to save the day. Perfect. So let's see what's the best version of it. It's here. Right, that's the rate at which I change the orbits considerably, time scale, or rate, inverse time. Right? Yes. Now, this is the time scale. If I go back to my diagram here, that I diffuse out of a circular orbit, that I change my circular orbit by order unity. But if I already have an extremely eccentric orbit, I don't need to change it by that much, because the periapse is already tiny, so the time scale to change the periapse is smaller. Since it's a diffusive process, it's smaller by the square of the angular momentum. And since the angular momentum is the square root of the periapse distance, square of the angular momentum is just proportional to the periapse distance. So I'll multiply this by Rp over R. So I remind you, this is a function of R. It's the orbital period around the black hole. This is the distance from the black hole. This is the periapse distance from the black hole. And this is the number of stars with that R, which we calculated from the Bacall-Wolf profile. This one. Okay. Now we need the rate at which gravitational waves take an orbit like that and change the apoapse. Let's see if I can remember that. What do I remember about gravitational waves? I remember that if I have two objects of the same mass, both of them are black holes, and they are touching each other, many ifs. Two objects, same mass, black holes, almost merging. How long will it take them to merge by gravitational waves? One orbit. Okay. So for that particular case, it's the time is the Schwarzschild radius divided by c, because they're also moving at the speed of light, so one orbit is the crossing time. The rate of emission of gravitational wave is proportional to the mass square, but the energy that you have to lose is only proportional to the mass, and therefore, if you have a mass ratio between the two black holes, or the two objects that are in spiraling, the time is longer by this. Okay? So this is the time scale for merging of two objects. One is a black hole, and the other one is on its horizon. So the number of orbits it will have to do is m over m. Okay. For larger orbits, let's say of this size, Rp rather than R Schwarzschild. So this is for an orbit whose size is the Schwarzschild radius. Now I'm saying something for memory. Well, we can derive that too, but we won't have time for that. I know that the time scale goes like the distance to the 4. So I have Rp over the Schwarzschild radius to the 4. So this is the time scale to shrink a circular orbit whose size is Rp, rather than the Schwarzschild radius of the supermassive black hole. But that's not what I need. I have an elongated orbit. Its shorter distance is Rp, but I actually only want to shrink the apoapse. It requires much less emission of energy, so therefore shorter time scale by Rp over R. But each orbit takes longer by R over Rp to the 3/2. So this is my convoluted way of doing it. You can do it in other ways. This is the gravitational wave timescale. So now you compare that and that, except this is an inverse, but compare that to the inverse of that, and I promise you will get this line. Now it's just algebra, and we're out of time. Okay, thank you very much.